Inverse trig example. What I'm going to do is walk you through a question which maybe it seems quite similar to the ones you've you've done already. I'm going to walk you through it without using inverse trig. Okay? Grab a sheet. When we looked at that previous example, the plane flying overhead and the radar that was tracking it, if you remember that, I think we looked at it and we decided inverse trig was not a good way to go because you can solve it quite easily without inverse trig, and you have to differentiate, and differentiating inverse trig is gross. So I'm going to solve this question for you in a second without it because I think that's still the best way. However, I'm then going to show you how you would solve it with an inverse trig for two reasons. Number one, because you can. Number two, because you guys know sometimes exams have this pesky habit of prescribing a particular method that you have to use for a question, right? So even though you could solve it another way perfectly fine, and you know, induction's a classic example. A lot of the results that they ask you to prove, like say the calculus ones, way easier to prove without induction. But they want to see if you know what you're talking about and that you can actually use that skill in a place you might not usually. Okay, so that's what I'm going to show you how the question works. It's not that much worse, but I still don't prefer it. Okay, so I'm going to take a question straight out of the program. I'll read it for you first, just the whole thing, so you can get an idea in your head, and then I'll read it again slower so you can sort of get the key details and maybe draw yourself a rough diagram. We can start solving it. Okay, so here we go. A rope from the bow of a dinghy is attached to a winder, like winder, to a winder on the wharf. The wharf is 3 meters above the bow level of the dinghy. If the rope's being wound in at a rate of 2 meters per second, at what rate is the angle between the rope and the wharf decreasing when the dinghy is 4 meters from the wharf? Okay, did you catch all that? Alright, let's try it again slower. You've got a wharf and you've got a dinghy, okay? I am, now that I've stopped reading the question, I'm just going to call it a boat, because I don't know why, it's such a weird word. Anyway, so you've got a wharf, okay, and it's above the water. Okay, there's my wharf, and it's got a winder here, so like some, you know, it's got like a handle on it, which is attached to a rope, which is attached to the boat. Okay, so here's my boat. Okay, and this thing is reeling in the boat from its bow. There's the bow on the end. Okay. The wharf is 3 meters. Sorry, the wharf is 3 meters above the bow level of the dinghy. So we're calling this 3 meters. Okay. If the rope's being wound in at a rate of 2 meters a second. So they're turning this thing, right? And this guy is getting shorter and shorter and shorter. And I guess because, you know, it's not lifting it off because of gravity, this thing's actually moving in. But this guy is going 2 meters a second, I guess shorter, so towards that direction. Okay. At what rate is the angle between the rope and the wharf? The rope and the wharf. At what rate is the angle decreasing when the dinghy is 4 meters from the wharf? So that's this distance here. Alright, do you need me to repeat any parts of that again, or is that sort of enough? Is that okay? What's a dinghy? Alright, now, let's have a look at this. By the way, just as a minor detail, you can see I put this in as 3 meters, and I put this as 4 meters with sort of dotted lines. Can anyone suggest why I might do that, or why might you do that? Good. So this 3 meters is always 3 meters, whatever situation the question is dealing with. But this 4 meters, it's 4 meters at a particular time. That's the time I will be interested in later. Okay? So at one instant, it's 4 meters, and then it'll be shorter sometimes and longer other times. So I've just put that in dotted so that I can distinguish between those. Okay? Alright, so, where do we start? Well, usually I say, okay, what's given to us, apart from all of these measurements? Okay? Well, there was a rate given to us, and I need to be able to describe it in some terms, right? So this length here, which is changing, the rope, what do you think we should call it? L? I suppose you could call it L. I called it R for rope. Is that too different? I'm just going to go R meters. is for apple. Okay, you can call it L if you want. Like I said, it doesn't matter, right? Therefore, I've got that distance, the length of the rope, changing. So what's given to me is dr on dt. What is dr on dt? -2. It's getting shorter, yeah? Okay. So just another reason why you've got to be careful when you say this. Watch out for on your diagram when you put an arrow or something like that. You've got to make sure you know what direction it's going. Okay. That's given. What I want to find is, what do I want to find? Well, whatever this angle is, whatever you've called it, I've called it theta. So d theta on dt, how it's changing over time. So you know enough by this point. What do you put after here? Where do I go next? Chain rule, yeah. So I'm going to have d theta on. Now at this point you can probably say, what's the variable I'm going to be relating? Yeah, dr. It's the only other one I've got, right? And I'm going to multiply that by the rate that I know, dr dt. Okay. All right. So now what? What do I do? I'm going to have to bring some trig in, right? Because this dr dt quantity, I know, it's just that constant. But in order to get this one, I need some relationship between theta and r, between an angle and a side. In this right angle triangle, that looks like a side, doesn't it, in a right angle triangle? So, what's my relationship? Which one should I choose, do you think? I've got theta, and I've got to relate it to this side, which is the hypotenuse of this triangle, and then I get to choose. Right? So which side should I relate it to? This is one of the reasons why I put this in as dotted, right? You can't really use, well you can use this, except it's not really for, right? Actually, as a variable, because this changes as well as this, what would it be equal to? It'd be, well by Pythagoras, it'd be square root of r squared minus 9, wouldn't it? Is that right? Yeah? So I could use that, but why would I use that when I have something perfectly simple to choose from, which is a much better option? Okay? So, James. It's cosine, thank you. Adjacent and hypotenuse. We got there eventually. So I'm gonna get down here. Cos theta is equal to adjacent on hypotenuse. Okay? Now I said to you first, we would change this so that we avoided inverse trig. Okay? We'll deal with inverse trig in a second. So if I'm going to avoid inverse trig, what am I going to do here? What do I make the subject? I want r to be the subject, right? Then I can work out dr and d theta and then take the reciprocal. Okay? So if r's the subject here, I'm just swapping them, really. Okay? So there's r. Now when I take the derivative, that's sec theta. Does anyone know the result? Sectan? Is it sectan? Sectan? I don't think it is sectan. Is it? Yeah, I think we're going the other way. Should we just do it from scratch? Okay, let's just do it. I'm going to treat this as cos theta to the power minus 1. Okay, so when I differentiate this, chain rule, yeah. I prefer chain rule to quotient rule because I don't like the quotient rule. So dr on d theta is equal to, what's my first step? I'll just whack the 3 down. Yeah, is that okay? Now what? Power down, so minus out the front. I've got cos theta to the power of, reduce it by 1. Now what? Derivative of the inside, right? Chain rule, yeah? So I've got minus sine theta out the front. Okay. So, okay, minus 3. Oh, I know why. Sorry, never mind. Just thinking myself. That's a plus. And there's our cos squared theta. Okay. Now, that is sectan. Now, why didn't I go towards sectan? Because I actually don't want dr on d theta, do I? I actually want d theta on dr. So I'm going to take the reciprocal of this, and then I'm going to work with that. Okay? So if that's dr on d theta, Now when I come up to here and I substitute it in, just remember to take the reciprocal. So that's going to be cos squared theta on 3 sine theta multiplied by minus 2. So I'm just going to slap the minus 2 at the front. You happy with that? Okay, so there's our derivative. Now, this is the rate that theta is changing over time. I wanted it at a particular point. What particular point did I want? Which point was I after? Not just any point. Yeah, good. When this was 4, hence my dotted line, right? So the problem with that though is that it has nothing to do with theta, or not directly anyway. Okay. So if I know that this is 4, I want to know what cos theta and sine theta are, right? So I would say when I haven't given that a distance, but I can say when that's 3, this is 4. What's r equal to? 5. So when r is equal to 5, I can say cos theta is equal to, well, it's just 3 over 5, right? And sine theta is equal to opposite on hypotenuse, 4 over 5. Okay? So now these values I can take in. Okay? So when r is equal to 5, d theta on dt is minus 2 times all over. Is that okay? Alright, so let's simplify out a little bit. This is going to be 9 on 25. So I've got minus 18 on 25 on top. This is 12 on 5. Yeah. This 5 will make this a 5. I can go by 6, so this will become a 2, and this will become a 3, so I'm getting minus 3 over 10. Does that check out? Not slowly at me. Yes, no, I'm not there yet. It's okay. Hooray, great, our numbers. Now, minus 3 over 10, that was the question. Now, by the way, what are the units? Radians per second. Okay? Now, by the way, last time when we were thinking about the plane, right, I posed to you the question, why radians and not degrees? Did anyone think about it any further? I was too busy getting ready for dodgeball. That's okay. Let me explain. I won't give you the full explanation, but it's actually a lot simpler than you think. The reason why this is going to be in radians is because we're dealing with calculus. When you're dealing with calculus, you have to be in radians. Why? Well, I want you to see how far you can remember back when we were doing this. When we were proving this result, this is kind of your introductory calculus trig result, right? How did we prove it? There were 2 ways we went about it. Firstly, we looked at the graph and we said, well, it kind of, when you describe its gradient here is like 1 and its gradient here is like 0, and we sort of mapped it out, and you're like, oh, that looks like cos. So we knew it was sort of in that general direction, right? But that was not really a very, it's not a very vigorous proof. So if you remember, we did a vigorous proof and it had to do with this limit. I remember it. Sin x, x, 10x. Do you remember that at all? Vaguely ringing a bell. And so we established this limit. As x approaches 0, sin x on x is equal to 1. Okay? Now we needed that when we were doing first principles for this. Okay? But here's the kicker. Where did these results come from? Do you remember? They came from radian measure. They came from the size of an angle, and you had this circle, and there was a sector here, and it was getting smaller than the triangle was getting smaller than the sector, blah, blah, blah. You can look back in your notes if you want, but the key is that these results, which look like they're a graphing thing really, sine and then x and then tan, they really come from looking at the area of a circle in different parts of it, okay? So seeing as all of these results only work in radians, all of these results only work in radians, so all of these results only work in radians, so this only works in radians. It doesn't make sense if it's in degrees, okay? You have to multiply everything by 180 on pi, okay? Which I suppose you could do, but all of your numbers would be disgusting, okay? Alright, now, there's a solution, minus 3 over 10. How do we do it with the inverse tree? Which crucial step is different? Can you tell me? Yeah, good. At this point, actually, maybe even one before that, when I'm going for my derivative, instead of working out dr and d theta and taking the reciprocal, using inverse trig allows me to work out d theta on dr directly. Okay, so let me show you how it works.